Section 7.3, Sizes of Atoms and Ions. Size is one of the important properties of an atom or an ion. We often think of atoms or ions as hard, spherical objects. According to the quantum mechanical model, however, atoms and ions don't have sharply defined boundaries in which electron distribution becomes zero. Nevertheless, we can define atomic size in several ways, based on the distances between atoms in various situations. Imagine a collection of argon atoms in the gas phase. When two atoms collide with each other in the course of their motions, they ricochet apart, somewhat like billiard balls. This movement happens because of the electron clouds of the colliding atoms can't penetrate each other to a significant extent. The closest distances separating the nuclei during the collisions determine the apparent radii of the argon atoms. We might call this radius the non-binding atomic radius of the atom. When two atoms are chemically bound to each other, as in the chlorine molecule, an attractive interaction exists between the two atoms leading to a chemical bond. We'll discuss the nature of such bonding in Chapter 8. For now, the only thing we need to realize is that this attractive interaction brings the two atoms closer together than they would be in a non-binding collision. We can define the atomic radius based on the distances separating the nuclei at atoms when they are chemically bound to each other. This distance, called the bonding atomic radius, is shorter than the non-bonding atomic radius, as illustrated in Figure 7.6. Unless otherwise noted, we'll refer to the bonding atomic radius when we speak of the size of the atom. Figure 7.6. Distinction between non-binding and bonding atomic radii. The non-bonding atomic radius is the effective radius of the atom when it is not involved in bonding to another atom. Values of bonding atomic radii are obtained from measurements of interatomic distances in chemical compounds. Scientists have developed a variety of experimental techniques for measuring the distances separating nuclei and molecules. From observations of these distances in many molecules, each element can be assigned to bonding atomic radius. For example, the iodine molecule, the distance separating the iodine nuclei is observed at 2.66 angstroms. We can define the bonding atomic radius of iodine on the basis to be 1/2 of the bond distance, namely 1.33 angstrom. Similarly, the distance separating two adjacent carbon nuclei in diamond, which is a three-dimensional solid network, is 1.54 angstroms. Thus, the bonding atomic radius of carbon is assigned as a value of 0.77 angstroms. The radii of other elements can be similarly defined. For helium and neon, the bonding radii must be estimated because there are no known compounds of these elements. Knowing atomic radii allows us to estimate the bond lengths between different elements in the molecules. For example, the chlorine-chlorine bond length in chlorine molecule is 1.99 angstrom. So the radius of 0.99 angstrom is assigned to chlorine. In the compound carbon tetrachloride, the measured length of the carbon-chlorine bond is 1.77 angstrom, very close to the sum of 0.77 plus 0.99 angstrom of the atomic radius of carbon and chlorine. If we consider the radius of an atom as 1/2 of the distance between the nuclei of atoms that are held together by a bond, you may wonder why the spheres representing atoms seem to overlap in some drawings, such as in figures 1.1 and 2.20. These depictions of molecules are called space-filling models, and they use non-bonding atomic radius, also called van der Waals radii, to represent the size of different elements. Even in these representations, the distance between the centers of two adjacent atoms in the molecule is determined from bonding atomic radii, also called covalent radii. Figure 7.7. Trends in atomic radii. Bonding atomic radii for the first 54 elements of the periodic table. The height of the bar for each element is proportional to its radius, giving a relief map view of the radii. Periodic trends in atomic radii. If we examine the relief map of the atomic radii shown in Figure 7.7, we observe two interesting trends in the data. Number 1. Within each column or group, atomic radius tends to increase from the top to the bottom. This trend results primarily from an increase in the principal quantum number of the outer electrons. As we go down a column, the outer electrons have greater probability of being farther from the nucleus, causing the atom to increase in size. Number 2. Within a row or period, atomic radii tends to decrease from left to right. The major factor influencing this trend is the increase in the effective nuclear charge as we move across the row. The increasing effective nuclear charge steadily draws the valence electrons closer to the nucleus, causing the atomic radius to decrease. Periodic trends in atomic radii. Just as bonding atomic radii can be determined by interatomic distances in elements, ionic radii can be determined from interatomic distances in ionic compounds. Like the size of an atom, the size of an ion depends on its nuclear charge, the number of electrons it possesses, and the orbitals in which the valence electrons reside. The formation of a cation vacates the most spatially extended occupied orbitals in an atom and decreases the number of electron-electron repulsions. Therefore, cations are smaller than their parent atoms, as illustrated in Figure 7.8. The opposite is true for anions. When electrons are added to an atom to form an anion, the increased electron-electron repulsions cause the electrons to spread out more in space. Thus, anions are larger than their parent atoms. For ions carrying the same charge, size increases as we move down a column in the periodic table. This trend is also to be seen in Figure 7.8. As the principal quantum number of the outermost occupied orbital of the ion increases, the radius of the ion increases. An isoelectronic series in a group of ions, all containing the same number of electrons. For example, each ion in an isoelectric series of O-2, F-1, sodium +1, magnesium +2, aluminum +3, all has 10 electrons. Any isoelectronic series that we can list, the members in order of increasing atomic number. Therefore, nuclear charge increases as we move through the series. Recall that the charge on the nucleus of the atom or a monoatomic ion is given by the atomic number of the element. Because the number of electrons remains constant, the radius or the ion decreases with increasing nuclear charge as the electrons are more strongly attracted to the nucleus. Notice the positions of the atomic numbers of the elements in the periodic table. The nonmetal anions precede the noble gas neon in the table. The metal cations follows a neon. Oxygen, the largest ion in this isoelectronic series, has the lowest atomic number 8. Aluminum, the smallest of these ions, has the highest atomic number 13.